Welcome to this deep dive into Claude Code, Anthropic's agentic CLI for software development. Over the next 50 slides, we'll explore the full engineering architecture, how the master agent loop works, how skills package expertise into repeatable workflows, how memory persists across sessions, and how the Model Context Protocol connects Claude to the broader ecosystem of developer tools. We'll finish with a live walkthrough of the Superpowers skill system as a concrete example of all these concepts in action. Claude Code represents a fundamental shift in how AI participates in software development. The old model was simple. You ask, the AI suggests, you execute. Copilots improved on this with inline autocomplete. But Claude Code takes a third step. It's a fully autonomous agent that reasons, acts, and verifies its own output. Instead of bridging the gap between AI suggestion and file execution yourself, Claude integrates reasoning with action directly in your terminal, searching codebases, running commands, and iterating until the task is complete. The power of Claude Code rests on three foundational pillars. First, the agentic loop, a single-threaded execution engine that runs tool cycles reliably until a task is done. Second, the skill system, a way to package domain expertise into repeatable, automated workflows that transform a general model into a specialized expert. And third, persistent memory, a hierarchical, file-based system that ensures the agent never forgets what it learned in previous sessions. Together, these three pillars make Claude Code an orchestrator of AI-led engineering workflows, not just a code generator. Here's our roadmap. We'll start with the master agent loop and its architectural foundations, then move to the tool system and how Claude interacts with your codebase. After that, we'll dig deep into the skills framework, the heart of Claude Code's extensibility. We'll cover the memory architecture, the model context protocol integration, sub-agents and parallelism, the security model, and finally we'll spend significant time on the Superpowers skill system as a real-world example of everything coming together. Looking at the full system from the top down, users interact through a CLI, IDE extension, or web interface. Below that sits the core scheduling layer, the NO master loop, and the H2A async queue. The operational layer handles tool routing and context compression, and at the bottom the agent can reach built-in tools, skills stored in the .claude directory, MCP servers for external integrations, and the memory system through claude.md and memory.md files. Every layer communicates through text-based interfaces, keeping the architecture universal and debuggable. Part 1. The master agent loop. This is the beating heart of Claude Code, the mechanism that turns a language model into an autonomous agent capable of executing multi-step engineering tasks. We'll look at the NO loop, the H2A async queue for real-time steering, and how the context compressor keeps long sessions from running out of memory. The NO master loop follows a deceptively simple pattern. Evaluate the current context. Generate tool calls if actions are needed. Execute those tools in a local or sandboxed environment. Feed the text results back into the model's context window. Repeat. The loop exits only when the model produces a final text-only response, at which point control returns to the user. This while loop architecture is intentional. By keeping execution strictly sequential and linear, every step is traceable and debuggable. Why did Anthropic choose a single-threaded design? Multi-threaded agents have competing reasoning paths, hard-to-debug failures, state conflicts between threads, and non-deterministic behavior. By contrast, the NO loop maintains a flat message history. The agent knows exactly where it is at every moment. Its reasoning is linear and traceable. This architectural choice reflects a core principle. Simplicity enables reliability. The agent may be less concurrent, but it's far more predictable, which matters enormously in production engineering workflows. But if the main loop is single-threaded, how does real-time human steering work? That's where the H2A async queue comes in. It's a dual buffer queue that sits alongside the main loop. While the NO loop is executing a long-running task, the H2A queue accepts incoming user messages into a separate buffer. The user can interject mid-execution, providing new information, correcting a misstep, or changing direction entirely. The agent pauses, reevaluates its trajectory, and resumes, without losing the accumulated state of the session. Here's the full architectural stack laid out. The interaction layer uses Bun, Commander.js, and React Inc. to render the terminal UI. The NO loop is the single-threaded executor. The H2AQ handles event steering. The tool engine dispatches JSON tool calls. And the W2 compressor manages context at a 92% utilization threshold. Every layer communicates via text-based interfaces. Tool results are stringified before re-entering the context window. This keeps the architecture universal and debuggable, regardless of what tools are being called. Long agentic sessions fill up fast. File reads, bash output, tool results, reasoning chains, they all accumulate. The W2 compressor kicks in automatically at 92% context utilization and summarizes earlier exchanges while preserving key decisions and the current task state. The tech stack supporting all of this is notable. Bun provides compilation efficiency far beyond Node.js. React Inc. handles terminal UI rendering with ANSI escape codes, and Commander.js parses the CLI commands. This high-performance foundation handles the high-latency demands of large codebase exploration. Part 2. The tool system. Tools are the hands of the agent, the mechanisms by which Claude Code actually reads files, runs commands, searches code, and makes changes. We'll look at the built-in tool suite, how Claude avoids the context tax problem through programmatic tool calling, and why regex over the file system beats vector embeddings for code search. Claude Code ships with a comprehensive built-in tool suite organized into 3 categories: discovery tools, LS, view, glob tool, and grep tool. Let the agent map and search any codebase. Editing tools, edit, write, multi-edit, and notebook edit. Let it make precise changes. Execution tools, bash, agent, web fetch, and web search. Let it run commands, spawn sub-agents, and reach the internet. One key design choice: grep tool uses regex over the live file system rather than vector embeddings, ensuring the agent always sees the current state of your repo, never an outdated index. The 4 discovery tools form the foundation of how Claude navigates a codebase. LS handles initial project structure mapping. View reads specific files with structured output. Glob tool matches file patterns, finding every test file or every TypeScript interface in the project. And grep tool searches content with regex, finding every usage of a function, every occurrence of a pattern, every import of a module. The reason Claude favors regex over semantic search is important. Embeddings go stale between index builds, while regex always hits the live file system. No drift, no false confidence. Standard natural language tool calling has a serious problem: the context tax. Every tool invocation requires a full inference pass. If a tool returns 2,000 rows of expense data, that floods the context window and displaces the critical reasoning the model needs. Claude Code addresses this through programmatic tool calling. Instead of feeding raw results back to the model, Claude writes a Python script that orchestrates the tools, handles loops and conditionals, processes the data locally, and returns only the final filtered result. The context cost drops dramatically. Here's the key insight of programmatic tool calling. Control flow is explicit in code, not implicit in the chain of thought. Instead of the model having to reason through 2,000 rows of data in its context window, it writes a script that does the processing in a sandboxed environment. The script loads the data, filters it, aggregates it, and returns one number, the total. This dramatically reduces token consumption, makes the logic explicit and reusable, and improves reliability. The model isn't reasoning about the data. It's orchestrating code that processes the data. Part 3. The skills framework. This is the most powerful extensibility mechanism in Claude Code. Skills let you package domain expertise, deployment procedures, coding standards, and organizational workflows into repeatable, automated procedures that the agent follows consistently every time. We'll look at the anatomy of a skill file, how triggers work, composability, and how skills are distributed across engineering teams. A skill is fundamentally a packaged set of instructions and supporting files stored in the .claude/skills directory of a project. Without skills, Claude applies generic reasoning that produces inconsistent results. It has no knowledge of your organization's patterns or your project's unique architecture. With skills, the model transforms into a domain expert that knows your coding standards, follows your deployment procedures, and applies your team's best practices consistently. A skill directory typically contains a skill.md entry point, markdown templates, shell or Python scripts, and reference documentation. Every skill is defined by a skill.md file. This file uses YAML front matter to define metadata and markdown for the procedural body. The front matter separates the trigger, how and when the skill activates, from the content, what the agent actually does. In this example, the deploy staging skill declares its name, a description the model uses for automatic invocation, the software dependencies it requires, and the exact tools it's allowed to use. The body then walks through each step. Check the issue, run tests, build the Docker image, apply Kubernetes manifests, and verify the rollout. The front matter fields each serve a specific purpose. The name field defines the / command, so this skill is invoked as /deploy staging. The description field, capped at 200 characters, is what the model reads to decide whether this skill is relevant to the current task, making it the most important field for automatic invocation. Dependencies ensure the environment is prepared before execution. The disable model invocation flag prevents the agent from auto-triggering the skill, requiring explicit user commands. And allowed tools restricts what the skill's sub-agent can call, scoping permissions per workflow. Skills can be invoked in two ways. Manual invocation is simple. The user types a / command like /deploy staging or /commit, and the skill content loads immediately. Automatic invocation is more subtle. Claude reads the description field of every available skill and decides whether it's relevant to the current task. Tell Claude to fix a bug, and it might automatically trigger the systematic debugging skill. Start building a feature, and it might trigger brainstorming. The disable model invocation flag in the front matter gives you explicit control over which skills can auto-trigger and which require a human to invoke. The body of a skill file contains the expert workflow in plain markdown, checklists, decision trees, hard gates, error handling patterns, and output format templates. A well-designed skill body encodes the kind of procedural knowledge that would normally live in a senior engineer's head. For example, a GitHub issue skill might mandate: first understand the issue using the GHCLI, then search the codebase for relevant files, write a failing test before touching production code, implement the fix, and create a pull request. This procedural rigidity is intentional. It reduces the variance in LLM outputs and produces consistent results every time. Skills cannot explicitly call other skills. There's no invoke API within a skill body. But this limitation turns out to matter less than you'd think. The agentic loop itself acts as the composer. Claude can identify and use multiple skills in sequence to solve a larger problem. A typical workflow might chain the brainstorming skill, then writing plans, then test-driven development, then code review, each skill handling its phase with its own expertise. Supporting files in the skill directory, scripts, templates, reference docs, enable complex validations without bloating the markdown instructions. For enterprise deployment, skills ship as plugins. A plugin bundles a complete set of skills together with MCP server configurations, letting a team install organizational coding standards and deployment tools with a single command. This centralized approach to AI capability management is a key differentiator for enterprise adoption. Instead of every developer maintaining their own skill configurations, the organization publishes a governed, audited skill set that activates consistently across the entire engineering team. The plugin system is how skills scale from individual productivity to organizational standards. Part 4. Memory architecture. Standard AI assistants suffer from amnesia. Every session starts blank, forcing you to repeat context constantly. Claude Code solves this with a multi-layer Markdown-based memory system. We'll look at each layer: the always-loaded Claude.md briefing file, the agent-authored memory.md notebook, daily logs, and on-demand topic files. The amnesia problem is real and expensive. Every new session with a standard AI assistant means re-explaining the project structure, restating the coding standards, re-providing context about recent debugging breakthroughs. Claude Code addresses this with a hierarchical memory system, where different kinds of knowledge are stored at different layers. Some things are loaded every session. Others are written by the agent itself when it discovers new information. Others are loaded on demand when relevant. As a result, the agent behaves like a team member who actually remembers what happened last week. The memory hierarchy has 4 distinct layers. At the top, Claude.md and memory.md are injected into every session startup. They're always present. Daily logs in date-stamped Markdown files are written via the flush command and capture chronological work records. Project state is embedded in Claude.md comments, active threads, blockers, next steps. And topic files are deep domain knowledge loaded on demand via a routing table in memory.md. This hierarchy prevents context rot, where irrelevant historical data drowns out current task information. By keeping the most important context permanently loaded and the rest accessible but not forced. Claude.md is the primary channel for human-to-agent communication. It's the source of truth for the AI's behavior on a project, and is meant to be checked into version control alongside your code. Effective Claude.md files are concise, targeting under 200 lines, and well-structured with Markdown headers, grouping instructions on code style, testing frameworks, and architectural patterns. A powerful feature is the @import syntax, which pulls in other documents like readme.md or package.json dynamically. This ensures the agent always has access to the latest project manifests without duplicating their content. While Claude.md is authored by humans, memory.md is authored by the agent itself. It lives in the .claude/projects directory and serves as Claude's personal notebook. If the agent discovers a custom-build script, an undocumented API convention, or solves a tricky debugging problem, it writes that realization into memory.md. In subsequent sessions, those notes are loaded automatically. The system enforces a strict cap of 200 lines, or 25 kilobytes. When that limit is reached, the agent must condense earlier entries or move them to specialized topic files, preventing the memory from growing stale or consuming too much context. Part 5. Model Context Protocol Integration (MCP) is what turns Claude Code from a local coding tool into an enterprise-grade engineering participant that can reach your entire stack. We'll look at what MCP is, how the 3 transport methods work, how tool search scales to thousands of available tools, and see a concrete example of cross-platform orchestration. The Model Context Protocol is an open standard designed to solve the fragmentation of AI tool integrations. Before MCP, every integration was custom-built. Slack had its own, Jira had its own, GitHub had its own. MCP provides a standardized interface, like USB-C for AI agents, that any tool or data source can implement once and be accessible to any compatible agent. Claude Code can now reach GitHub, Jira, Notion, Slack, Sentry, local databases, internal APIs, and any custom MCP server your team builds. The integration cost drops from weeks of custom work to a single configuration. Claude Code supports 3 transport methods for MCP servers. Remote HTTP servers are the primary method for cloud services like Notion, Slack, or Sentry. The agent connects to a hosted MCP endpoint over HTTPS. Local STDIO servers handle tools that need direct machine access, like a local database or proprietary CLI, running as local processes communicating through standard input and output. And remote server-sent events is a specialized transport for legacy services that require real-time notifications. This flexibility lets the agent connect to both modern cloud APIs and legacy internal systems using the same protocol. In an enterprise environment, an agent might have access to thousands of MCP tools across dozens of servers. Loading the schemas for all of them would instantly deplete the context window. Claude Code solves this with just-in-time tool discovery. When the model encounters a task it can't solve with native tools, it queries the connected MCP servers for relevant tools based on the current context, loading schemas only for tools it actually needs. This allows the agent to scale its capabilities to thousands of available tools without a linear increase in context cost. It's the key to enterprise-grade MCP deployment. Here's what MCP makes possible in practice. A developer says, add the feature described in JIRA issue 4521 and create a pull request on GitHub. Claude Code uses the Jira MCP server to fetch the issue description and acceptance criteria. It uses local tools to search the codebase and implement the changes. Then it uses the GitHub MCP server to create a branch, push the code, and open a pull request with a generated description linked to the Jira ticket. One natural language command triggers a complete engineering workflow spanning multiple platforms. No manual coordination required. Part 6. Sub-agents and parallelism. For tasks of exceptional complexity, or those that require exploring multiple divergent paths simultaneously, Claude Code delegates work to sub-agents. These are isolated instances that run with their own context, protecting the main conversation from context exhaustion while enabling parallel exploration. Sub-agents are spawned via the dispatch agent tool. The primary motivation is context isolation. Agentic tasks, especially wide-scale code exploration, fill the context window rapidly. By delegating to a sub-agent, the lead agent keeps its own context clean, while the sub-agent handles the heavy lifting in isolation. The sub-agent completes its task and returns a summary to the lead. Multiple sub-agents can run in parallel, exploring different solutions simultaneously. This architecture is what enables Claude Code to handle genuinely complex engineering tasks that would exhaust a single context window. Part 7. The security model. Claude Code handles real code and real infrastructure, which means security is non-negotiable. The security model combines permission tiers that control what the agent is allowed to do with oxygen monosulfide level sandboxing that enforces those permissions at the kernel level. Claude Code's security is layered. At the permission level, there are 3 tiers. Default mode prompts the user before risky operations. Auto mode allows all operations within the sandbox, and plan mode is read-only with no execution. These can be overridden per tool in configuration. Below permissions, OS-level sandboxing enforces access at the kernel. macOS uses seatbelt sandbox exec to restrict file system and network access, while Linux uses landlock LSM. And, at the skill level, the allowed tools front matter field restricts which tools a skills sub-agent can call scoped permissions per workflow, not just globally. Part 8. Superpowers skills. This is where everything comes together. Superpowers is a production skill plugin that layers structured, disciplined workflows on top of Claude Code. It's the best real-world example of how the skills framework transforms agent behavior, making Claude more consistent, more rigorous, and more reliable across the full software development lifecycle. Superpowers is installed as a plugin. Its skills live in the .claude plugins cache and are loaded automatically at session start through the system reminder injection mechanism. The meta skill of the system is called Using Superpowers. It's loaded at every single session and does one thing: teach Claude how to use all the other skills before any work begins. It establishes the rules of engagement, which skills exist, when to invoke them, and critically, that skill invocation must happen before any response, including clarifying questions. The Superpowers catalog is organized into 3 categories. Process skills govern how Claude approaches work: brainstorming, systematic debugging, writing plans, and executing plans. Quality skills enforce rigor: test-driven development, verification before completion, requesting code review, and receiving code review. Execution skills handle the mechanics: dispatching parallel agents, using Git work trees, finishing development branches, and sub-agent-driven development. Notice the versioning in the plugin cache path. Superpowers /5.0.6/skills. Skills are treated as version software artifacts, not ad hoc instructions. The Using Superpowers skill establishes a strict priority order. User instructions from Claude.md or direct requests come first, always. Superpowers skills come second, overriding default system behavior. And default system prompts come last. The core behavioral rule is unambiguous. If there is even a 1% chance a skill might apply, invoke it before any response. Not after gathering context. Not after asking a clarifying question. Before anything else. Skills are categorized as either rigid, like TDD and debugging, which must be followed exactly, or flexible, like pattern-based skills that can be adapted to context. Here's the exact invocation flow. A user message arrives. Claude scans all skill descriptions to assess relevance, even at 1% probability. If a skill matches, the skill tool is invoked, and the full skill content loads into context. If the skill includes a checklist, Claude creates a task item for each step using the Task Create tool to track progress visibly. Then it follows the skill exactly and responds. The key insight? The flow checks for skills before doing anything else, before gathering information, before exploring the codebase, before asking questions. Skills define how to do all of those things. The brainstorming skill is a perfect example of a rigid process skill. It governs all creative and implementation work, and its hard gate is absolute. Do not write code, scaffold any project, or take any implementation action until a design has been presented and the user has approved it. This applies to every project, regardless of perceived simplicity. The process runs 9 steps. Explore project context, offer a visual companion, ask clarifying questions one at a time, propose 2 to 3 approaches with trade-offs, present design sections for approval, write the spec to a docs directory, self-review the spec for TBDs and contradictions, wait for user approval, and only then invoke the writing plan skill. The Using Superpowers skill explicitly lists the rationalizations that lead to skipping skills, calling them red flags. This is one of the most insightful parts of the system. When Claude thinks, this is just a simple question, that's a rationalization, because questions are tasks. When it thinks, I need more context first, that's wrong, because skill checks come before gathering context. When it thinks, I remember this skill, that's dangerous, because skills evolve and the current version must be read. When it thinks, this doesn't need a formal skill, that's wrong if a skill exists. The explicit enumeration of failure modes is what makes this system robust. When multiple skills could apply, 2 rules govern priority. Process skills come first. If the user says, let's build something, brainstorming activates before any implementation skill. If the user says, fix this bug, systematic debugging activates before any domain-specific skill. The second rule is equally important. User instructions specify what, not how. If a user says, add feature X, that describes the goal. It doesn't authorize skipping the brainstorming workflow that determines how to implement it safely. This distinction between what and how is what prevents the agent from taking premature action on underspecified requests. Here's how all 8 systems work together in a single workflow. A user asks Claude to add the feature from a Jira ticket. The Superpowers brainstorming skill activates. The user approves a design. The writing plan skill creates an implementation plan. The Jira MCP server fetches the ticket requirements. The TDD skill mandates writing a failing test first. The NO master loop executes the implementation cycle. The agent writes its learnings to memory.md. And the GitHub MCP server opens a pull request. 1 request. 8 systems. Complete engineering workflow, end to end. 5 key architectural insights to take away. First, single-threaded by design. Simplicity enables reliability in the NO loop. Second, skills encode expertise, not just instructions. Procedural rigidity reduces LLM variance and produces consistent results. Memory prevents context rot. Hierarchical persistence with enforced caps keeps the agent's knowledge fresh and relevant. Fourth, MCP standardizes integrations. Just-in-time tool discovery scales to thousands of tools without context cost. Fifth, skills are behavioral contracts. They override defaults but always defer to explicit user instructions. These aren't just implementation details. They're architectural principles. Perhaps the most profound implication of the Claude Code Architecture is what it means for the developer's role. The old role was manual implementation. You bridged AI suggestions to files, repeated context every session, and used one tool for one task. The new role is orchestration. You define skills and standards, review and steer rather than implement, and architect multi-agent systems. Claude Code's architecture is designed so that the developer's leverage multiplies, not their workload. The intelligence of the system scales with the quality of the skills, memory, and MCP integrations you build around it. Claude Code is not a tool. It's a new class of engineering participant, one that reasons, acts, remembers, and learns. The master-agent loop provides reliable, autonomous execution. The skill system packages expertise into consistent workflows. The memory architecture ensures continuity across sessions. And MCP connects the agent to the full engineering stack. Together, these four systems represent a genuine shift in how software gets built. Not AI that assists developers, but AI that participates alongside them. Thank you for watching this deep dive. The HTML slide deck and all source files are in the dev directory.